Hi, my name is Zeke, KJ7 and LL. And before we begin, I'd like to thank Steve at Qorvo for supporting us on our project with the LNA. We're trying to put an LNA at the base of the antenna because the antenna is like a stick if it's an end fed. But the antenna, you want it at the base of the antenna because you see the signal is coming into the antenna, but there's a lot of loss in the feed line. So as it gets to the radio, the loss in the wire can make it so that the LNA doesn't read as much if it's in the radio. But if it's at the base of the antenna, then we get the signal right off the start of the antenna, and that is why we're doing the project here. Now, we're going to share our screen. This is the data sheet for the QPL9547. As you can see, now our frequency is 144 to 148, and this is 0 to 1000. We want this to be negative 30, and it only goes up to negative 20, but as you can see here, it goes to 144 to 148. That's like right in here, and that is horrible, which is why we are optimizing the matching circuit. So is S22, because S22 is right here, and this is still 0 to 1000, so 144, 148. Well, it's not so good. And the gain's actually pretty good, but for the 440. Other than that, at our frequency range, it's also 20, which is also very good, but not nearly as good as it would be if we were in the 440 range. So that's like 25, 27. Okay, move this over here. So we're going to file new project. Okay, so I named it Tutorial LNA 1 because this is a tutorial on how to do the LNA. We have the original on this monitor over here. But I'm showing you how to do it. So, project, and we'll go to circuit schematics, new schematic, and we will call this the LNA 144 MH and little z. Okay, now we will project, data files, new data, import data file, import data file. We will go up to Touchstone and do the QPL9547 SN1. Now, they were dashes, but it doesn't allow dashes, so just click OK when this warning is. You don't really have to read it. Now we need to do Control L and type in QPL. Let's make this box smaller. What do you say? QPL. So it's actually Control K. I was wrong about Control L. Control K is for circuits. Control L is for premades. So Control K, and there it is. Okay, put it right there. Now, as you can notice, there is no attributes here for this. Like, you can't type anything in. That's because you change all the stuff around it, and the magic sauce inside. It's not really magic sauce, but whatever you want to call it. It's a black box, and you put stuff in, and it comes out. So all the stuff around, like this stuff has a lot of frequencies here. Like if I double click it, this is for every frequency that we might have. These are all the numbers that it has. So that it has been entered in. So now we will add a CL. So Control L, cap. Good. Now we will put this cap here, and shift click immediately draws a line. Now we'll make a port for port 1. Now we're going to do Control L, IND, and put the inductor here, and Control G for ground, put the ground here. Now we have port 1. Now for port 2, we are going to do a Control L. Actually, we don't need to do that. We can just copy, Control C, Control V, and put a port 2. Now we're not going to do that. Control right click rotates. And actually, we are going to copy this capacitor. It is not going to be an inductor this time, because this is port 2. Okay, the voltage source here, which will go here, we're not going to put it in because this doesn't need it, or we could just for reference, but it's not going to do anything. This capacitor is here because we don't want DC. This is like a battery. You ever put metal on either side of a battery? It could catch the battery on fire if it's high enough voltage. Or let's say you put an LED just between the positive and negative of ends of a battery without even putting a resistor. It's a resistor. Had it on my desk. So you don't want all the DC to go to ground, and DC will never go through a capacitor because, as you can see, DC is a square wave. It will never go through a capacitor. As you can see visual here, a capacitor has 2 plates, one on top, one on the bottom, and yeah. So home is everything. We will now Control G, ground, and do copy this, and now we will right click, and this stuff seems to just always be better underneath. It's just how it works a bit better. And we will copy this, put it here, ground this, and copy this with the ground, and shift click it right there because that draws a line. Now we are going to do Control L, RES for resistor, close form, go down, and Control G, ground. Then we're going to do Control L, CAP, capacitor, close form, and Control G for ground. Now, you might be wondering why in the world is there a resistor right here? Well, there's a third port, but when we download it, there isn't a third port. There's only port 1 and port 2. Only 2 ports. So this goes into right here, but there isn't a port there, and we don't know what happens in there. There's nothing there. So we suspect that at some point it just goes to ground. I mean, so that's why it's grounded, and there's a resistor here, so that we just call a resistor. And so now I'm going to do Control L, DCVS. Now, like I said earlier, this won't do anything. It's just for reference to help us remember what will go on in the real schematic. Control G, ground, and now we have this. So we're going to do project circuit schematics, new schematic, and we will call this one LNA test. Now the LNA test is very simple. We have two ports, a port 1 and a port 2, not connected because Control K should get us our sub-circuit. And this is what we will be optimizing here. Now, we will do view and, well, let's just do 6 and optimize everything but the ports. So we can do sort by ID, C1, C2, C3, C4, C5, C6. Now, R1. Now, these are not actually numbered like this, but if you were doing this, and since this is a tutorial, it would take a bit for me to rename everything to what it's actually on the schematic. But if you were going to do something like this of your own, you would probably want to make these IDs match the thing on the schematic. Now, lower and upper for all of the capacitor is going to be 1 to 1000. And so we can just do 1, 1, 1, 1, 1. And for the resistor, it's going to be 1. Now we can do Control A, Control C, Control V. Enter, Control C, enter, Control A, Control V. Control V, enter, Control V, down, enter, Control V, down, enter, Control V. And we do that for all of the capacitors. Okay, and for this, it's going to be 3.3 K. Okay, fine. Instead of K, we're going to do 33,000. Because in testing, that is what we found works. So now since all these are optimized, we are also going to constrain everything except for the ports, which are, but we do need to optimize the inductors, so this will be 1 to 1000. 1 to 1000. And we can unconstrain the ports and the voltage source. Now the voltage source's value will be 5 because that's what it's actually going to be. But like I said, this is just for reference, so it doesn't really matter. It does change it here. It doesn't really matter. Okay, now we will go to now we need to go to project, yield goals, add yield goal. So I just realized that we need to have some graphs before we can do optimizing. So new graph, rectangular, and we will call this LNA test. Right click, add new measurement. This is going to be S11. Okay. And right click, add new measurement. So we are going to do S21 now, because we already did S11. Now we need to go to Project, Optimizer Goals, add Optimizer Goal. This is going to be the 1-1, and 1-1 has to be less than -30. Okay. Now we will optimize our goals, add optimizer goal. It's going to be a 2-1. Now we want this greater than 20. Okay? Or actually, well, that's fine. It's log scale. Now, this is not the frequency range that we want. This is optimizing for the 144 to 148. So we're going to change that to megahertz, and it already is. And 0.1, apply. We have 41 points now. Okay. And now it is time to hit F7 on your keyboard and choose an optimization. So pointer gradient optimization will just go downhill, and if there's a hill, it'll stop. And try to get back out, but maybe can't quite get out if the hill is too high. So start, 50,000 and wow, look at that. That is going so fast. So it could take a bit for it to do the first thing. So I'm going to pause the video here and show you what we got. Actually, I'm just going to pause the video and see you when it is done. See you in a couple minutes. So I figured out a few things while the video was paused. One of the things was the L's were not being optimized, the inductors were not being optimized, and R1 was not actually supposed to be optimized. It was just supposed to be 3300 and not 33,000. So we are going to hit start, and I've got this set up so this is going to go really quickly, so you can watch the graph as we start it. And so this is going to go. So it's going really fast. See? It's just going to go really fast down here. And we converged. Yep. So now we are going to try it for the 440 band. So to do that, we are going to right click on this and duplicate. Now we have one more sub-circuit, and we are just going to change options, project options, from, and we need to change this to megahertz, from 420 to 450. 420 some areas cannot use, so we're actually going to do 430. And step 1 megahertz, apply 21 points. Okay, now all we need to do is change our test. So you can double click this, pull down, and LNA megahertz. And this is not going to be 144 megahertz anymore. This is going to be LNA 430 megahertz. Well, 440 megahertz. Okay. Now I'm gonna control zoom out so it's a tiny bit easier to see and not all too big. And now what we need to do is just hit the start button on the optimizer again, so we can close this. So we need to unoptimize because otherwise it'll optimize both, which will be crazy. So we are going to do Alt-6 and unoptimize filter by 144, and we will check, uncheck, and now you can see backspace, everything but always, and it kept our constraints very nicely there. So now our LNA test is set 440. So we can close all this, close this, and hit optimizer, or this, and window, title vertical, and now you can see both of them. So we're going to hit start, and then we're going to add just a big jump from 20 dB to 40 dB and see if it can get there, and also do negative 50 down here. And since it converts fast, I wonder if it will be able to get those insane numbers. Okay, let's go. Right. So, project goals. And so we need to add measurements now. And we're going to just double click this for properties. And this is not 144 anymore. It is going to be LNA test. And this is also going to be no more. It's going to be LNA test. Okay, time for starting optimization. Right. So now we need to change the goals because that changed what we need to select on the goals. So see, that's 144. So we need to select test 11 is negative 30. And that's what we want for a 11. And here, 21, 11. This is 21. Guess I got that backwards. This is negative 30 and less than, and 11. Okay, guess it got kind of confused there. So now it's ready for optimization, and it's very simple. All we need to do now is click start. Ooh. It got our numbers for the 430 to 450 band. Now, what we're going to do is just change these goals a bit to 11 negative 50 instead of 30, and 21 positive 40 instead of 20. Okay, now this is going to show you how good these numbers really can get. Now watch. It's gonna go, this will take a bit longer because it might be stuck in a pit right now. So we need something a bit more jumping around now, like simplex. So this will jump around a bit, and it's getting a lot better, as you can see. So now what we need to do is change it to pointer, and hopefully it got us out of that valley there. So we're at 500 iterations. This might be the best it can get with 30, 27, and well, it's trying things. Short iterations will show you what it's really doing. It's horrible. Okay, I think this is the best that it can get. So F8, will do a simulation for us. This is the best it can get without optimizing overnight. Yeah, so that is how to match a LNA circuit and make it work with the optimizer. So thank you for watching, and I hope you have a great day after you watch this video.